in the previous lecture we were in a position to discuss about the assumptions behind the Bernoulli's equation, and to continue with that I will write the form, the general form from which we wanted to derive it as a special form. So, from here if we write straight away with a question mark that what are the assumptions behind this, such that we can write so what are these question marked things. I will just recapitulate the entire thing so that it is a summary of the entire derivation. First we started with inviscid flow. So the first assumption is that it is inviscid flow, that is the most important assumption, most fundamental premises of all these equations. The second is the gravity is the only body force which is acting along the negative z direction. That also has to be defined because there might be other body forces, and in that case this equation might look different. Then steady flow will lead to this term equal to 0, rho equal to constant will make this switch in and out of the derivative without any problem, and finally this term has to be set to 0. So we identified 3 realistic cases. One is that dl is along a streamline, the second is the vorticity is a null vector, that is irrotational flow, and third is v cross omega is perpendicular to dl. When it is irrotational flow there is no restriction on dl, and therefore these are any 2 points 1 and 2. When it is not irrotational flow, if it is along a streamline, if v and dl are in the same direction, then 1 and 2 must be located on the same streamline, and if v cross omega dot dl is null vector, that is v cross omega is perpendicular to dl, then the points 1 and 2 should be chosen in such a way that that will be oriented along that dl direction. Okay. So now the next issue is that given, well, we all know that this is the Bernoulli's equation, and I am not spending a lot of time here on what it is and why it is important, but essentially it looks like that it is a equation conserving mechanical energy. So that effect is more clear if you now divide all the terms by g, which is also a form that is commonly used by hydraulic engineers. So here all the terms in the Bernoulli's equation are written in terms of length unit. Okay. So this length unit is essentially what does it represent? So let us write one after the other. So this is mgz1 divided by mg. So what is this? This is the potential energy, this is weight. So potential energy per unit weight. Because all the terms are of the same dimension, then all these represent some energy per unit weight, and energy per unit weight in hydraulics is called as head. So this is called as potential energy head. Okay. Similarly, this is kinetic energy per unit weight. So, these two are pretty clear, and we all know that mechanical energy is essentially sum total of kinetic and potential energy, but a third component comes to the mechanical energy here. So, what it is? Loosely books call it pressure energy, but we have to understand that fundamentally what it is. We can give it a name pressure energy, there is nothing wrong with it, but the name should better clarify the concept behind this term. So, to do that, let us assume that there is a pipe, there is some fluid which is ready to enter the pipe. Now, when you have to maintain a flow, you have to maintain the flow in presence of a pressure of an already flowing fluid, right. So, the fluid flow is maintained not by pushing this in a vacuum, right, there is already some fluid. So, there is already some mob and you have to enter a particular shopping mall, see how difficult it is instead of a vacuum where you are entering. So, here you have let us say a length delta x. Why I am calling a small length is because over that the pressure may be assumed to be not changing. Then the work done by this force to penetrate by this amount delta x, so that the flow can be maintained, is P into delta x into A. This per unit weight is this. So, P by rho g is the work done per unit weight to maintain the flow in presence of pressure. This is called as flow energy or flow work. So, this much of additional energy the systems should have to maintain the flow in presence of pressure. So, this is the difference between a stagnant system and a flowing system. So, if there is a system which is flowing, it should have sufficient energy so that it can maintain the flow in presence of pressure. So, this is flow energy or flow work. So, in a flow, based on the assumption sum total of this kinetic energy, potential energy and flow energy transferred between one point to the other remains conserved, not possessed, because there is a continuous flow process, this energy is not being possessed by the fluid, it is just instantaneously transferred from one point to the other, then from that point to the next point and so on. So, what is conserved is not that sum total of this energy possessed, but sum total of this energy transferred, that needs to be fundamentally understood. With this background on Bernoulli's equation and Euler equation, let us try to work out a representative problem which will illustrate some of the very basic concepts of this. I remind you that in the lecture classes we may not be able to cover many problems because of the time constraints. So, that in addition to these 40 lecture slots, whatever will be the tutorial slots and the supplementary material slots, those will be mainly for problem solving purpose. Given that, I am also trying to supplement that with one or two conceptual problems on each topic. So, let us consider a problem. Let us say there is a flow field where A is constant, a two dimensional flow field, and the objective is to calculate the pressure difference between 2 points 1 and 2 in the flow field. The assumptions are inviscid flow, rho constant and g along negative z. Okay. So, with all this we can write and A and V are not functions of time, so it is as good as steady. There is no W, so I am omitting the W part. Okay. Yes, right. Now, because it is steady flow, this is 0. These derivatives are so easy, we can quickly calculate. So, this is Ax, this is A, this is minus Ay, this is minus A. Oh, del y, sorry, right, very correct. I was mistakenly taking it as V. So, this is 0. So, you have this is equal to A square x, right, rho A square x. So, if you integrate this, plus this is a partial integration with respect to x, right. So, this if integrated with respect to x, it will be function of y and z, right. Z dependence is also there for pressure because there is gravity force, right. Similarly, so here this is 0, this part is 0, so this is V is minus Ay and this is minus A. What is the third equation? W is not there, so 0 is equal to minus right. So, essentially this is an equation of hydrostatic pressure variation or fluid statics. That is why these days there is a pedagogical development that people do not teach fluid statics as a part of many courses, because fluid statics, which was traditionally being taught as an integral part of many fluid mechanics courses, now the equations can be recovered as a special case of fluid dynamics when you set certain terms to 0, So, maybe because of time constraints and because of the fact that within the time constraints we have to introduce certain modern topics like atmospheric flows or micro nanoscale flows, which in earlier times were not there in advanced courses. So, we have to compromise for that in some way or the other, and this can be a good compromise. So, with this, so you will have P is equal to so if you compare these three, you can easily write that P is equal to minus rho function of yz will be this one. Interestingly, you can write this okay, you can also add another constant to it, the function itself may have some constant. So, interestingly you can write and this is, so essentially it is like the Bernoulli's equation that is being valid over the entire domain, and that equation governs the pressure difference between 2 points. So, you could clearly write P2 minus P1. So, you write P1 is equal to this P1 plus half rho V1 square plus rho G Z1 is equal to P2 plus half rho V square V2 square plus rho G Z2. From that you can get P2 minus P1. So, this problem is as simple as that, but the fundamentals of this problem can give a lot of insight. So, for most people the problem solution ends here, but for me the problem solution begins here. It is, as a teacher I always remember that solving a problem does not necessarily mean coming up with a final answer, but the insight that you learn from that problem is the lesson of your life, and that you have to understand very carefully. So, in this problem we are seeing that we could do it, solve it in two ways. One is integrating the inviscid equations of motion, another is directly writing the Bernoulli's equation, and these two solutions are converging to the same final answer. Now, the question is that why in this case it does so. So, one of the reasons is that this flow of course is inviscid flow and it is also irrotational flow. So, inviscid plus irrotational. Why it is irrotational? Let us calculate the kinematic parameters. So, u is equal to ax, v is equal to minus ay. So, you have this means the rate of angular or shear deformation is 0. So, if the original fluid element is like this, its angles will not be distorted. Not only that, this is a very interesting problem where you have this also equal to 0. That means it also does not rotate. Angular deformation is 0, that means the angles remain the same, but still it could have rotated like a rigid body. but that is precluded because here you have this equal to 0. So what will change? So something else remains conserved if you write this. Its volume is also conserved, but the partial derivative of u with respect to x is not 0 and that v with respect to y is also not 0. That means there will be stretching of one side and compression of another side such that the volume remains conserved. And what will be the equation of the streamline? So ln x is equal to minus ln y plus some ln k. So that means xy is equal to k, which is a rectangular hyperbola. So if you try to visualize how this fluid flow is taking place, imagine that there are rectangular hyperbola like this and the fluid element. So first the fluid element has small length, so large height, then assume that it is moving like this, then it is stretched along x and therefore it is compressed along y so that its volume is conserved, right. This is the typical visualization of a fluid element which does not distort and which does not rotate. And because it does not rotate, if it is inviscid, and the reason is that the combination of these two, why it is important is because it does not rotate initially, say starting with here, but because it is inviscid it does not rotate forever. So this brings us to the question that is it possible that a flow that does not rotate initially but starts rotating after some time? Yes, that is possible, and there are certain factors which can make an irrotational flow rotational. So one of the factors, clear factors, is viscosity. So we will first learn that what are the factors which can make an irrotational flow rotational and explain why that happens. So I will list down the factors one after the other, and the first obvious pointer is viscosity. Viscosity, thermal stratification, shock waves and Coriolis effect. So I will explain what these are, but the most important factor is viscosity. Imagine that you are there in a moving bus. When you are there in a moving bus and you are trying to come out of the bus near to a stoppage, those of you who are not from India and listening to this lecture, you might think that this is something absurd, that bus has not come to a stoppage but somebody is coming down the bus, but you know this picture, I mean seeing is believing. So then when this person is trying to come down from the bus, the experience of the person says that he or she has to run a bit in the direction of the bus immediately after coming down, so as to adjust with the previous inertia. If the person does not do that, there is a tendency that the person will topple. Why the person will topple? Because the person had an inertia because of the movement of the bus, suddenly the person is restricted by the ground, which is trying to bring the person to a standstill. So when this is happening, there is a chance that there is a rotation and the person will fall down. So the very fact that there is viscosity, that creates a disturbance to the momentum. In this case, the ground creates a disturbance to the momentum of the person. So when there is a disturbance to the momentum, there is a rotational effect that comes into the picture. So because of viscosity, there is a rotational effect. So that is why we are not just satisfied with saying a flow to be irrotational, we say inviscid plus irrotational. The reason is that although it is initially irrotational, it may not remain irrotational forever until and unless it is inviscid. So inviscid plus irrotational flow means it remains irrotational forever, that means the velocity potential is defined forever, and such a flow is called as potential flow. Thermal stratification means because of the temperature variation, there is a density variation and the lighter fluid gets settled at the top and the denser fluid gets settled at the bottom. Shock waves essentially are discontinuities. So in a domain where there is a very high speed flow, typically the speed of the flow is greater than the sonic speed or the speed at which the disturbance propagates. So at that very high speed, what happens is that the fluid, or in this case the object, say an aircraft moving relative to a fluid, moves faster than the speed at which a disturbance can move. Therefore the disturbances accumulate along a particular line which is called as a shock wave front, and there is a release of this discontinuity, release of this through a discontinuity across of the properties across the interface. This is called as a shock wave. So that will make a transition of flow from supersonic to subsonic, that is the flow speed will eventually become less than the speed of sound. So that one, and Coriolis effect, we will discuss about this in some details later on, but this is such an effect because of which, for example, the ocean current in the northern hemisphere moves in a certain direction and in the southern hemisphere moves in another direction, and fundamentally it is because of a force that is being felt when there is a translation of a particle in a reference frame that is rotating. So this results in a sidewise force, and under all these conditions an irrotational float will start rotating. So all these effects need to be kept in mind. The next point which we will touch upon in this particular lecture, and we will illustrate through an example in the next lecture, is the unsteady version of the Bernoulli's equation. So in the Bernoulli's equation, we neglected this term by assuming the flow to be steady. Now if the flow is unsteady, it is just a matter of adding this term. So there are two cases which we will study. Case 1 is dl along a streamline. If dl is along a streamline, let us say ES is the unit vector along the streamline and S is the streamline coordinate. S is streamline coordinate and ES is unit vector along the streamline. So, if you integrate the equation, it is a matter of adding this term but one criticality is that because streamlines themselves may vary with time in an unsteady flow, thus this streamline coordinate might have shifted from one streamline to another. So, with that as a factor kept in mind, at least the streamline pattern should not change, so that this differential direction changes altogether. It is possible to integrate this in a straightforward way for an unsteady flow. The second case is that irrotational flow. That means V is gradient of a scalar potential phi. So, this is so this becomes so it nicely fits in the differential form of the Bernoulli's equation, because there is d of p by rho plus v square by 2 plus gz. In addition to that, you have d of del phi del t. This you can write only if it is irrotational flow. So, with these two special cases in mind, in the next lecture we will work out a problem where through which we can illustrate the use of the unsteady Bernoulli's equation. Thank you very much.